Hello, we are the GVSU 2021 Senior Design Team 5, and we are working on the EMC PCB Design Study Project sponsored by E3 Compliance. Currently at E3, when a customer has a product that fails EMC regulations, it is the company's job to iteratively tweak and test the designs to determine what needs to change in order to get the product to pass regulations. As EMC is a relatively new field of specialization, customers will often bring production-ready products to E3 without having considered EMC during the design phase, potentially leading to substantial losses in time, resources, and money. Our goal is to compile a comprehensive, data-driven report which identifies how specific PCB design decisions will impact EMC. The study will provide E3's customers with the evidence to improve their product's EMC performance by implementing specific design changes with data to support the projected results. 2 devices are designed, each with multiple variants that differ in signal routing and grounding techniques. As per sponsor requirements, the main features of each component of the project are as follows. The electrical aspects of the project include 2 functioning circuit boards. The first PCB is designed to measure the DC voltage of an external device between 9 and 16 volts, as well as use a thermocouple to measure temperature between 15 and 100 degrees Celsius. This analog measurement board is commonly referred to as PCB1 for the sake of this project. The second PCB is configured to accept 12 volts DC from an external power supply and in turn deliver up to 15 watts of power as requested by the load through a USB-C configuration. This power delivery board is referred to as PCB2. The mechanical aspects of the project include 2 types of enclosures, conductive and non-conductive. Both are designed to show the effectiveness of different materials for shielding the circuits from electromagnetic interference. Given the project specifications, 7 variants for PCB1 and 3 variants for PCB2 are built and tested. This requires consistent execution to ensure uniformity between each variant. As our design and prototyping phases took longer than expected, the testing process is streamlined to allow for board builds and EMC testing in the last month of the project. Boards will be tested under Radiated Immunity, Conducted Immunity, Radiated Emissions, and Conducted Emissions. We must be sure to have functioning devices with ample time to perform tests and analyze results. Conductive enclosure geometry and tool selection is significantly driven by the need to contact exposed copper on the perimeter of the outermost layers of the boards. Features are designed to be machined in-house and yield full contact without putting excessive pressure on the boards. This method of grounding to the enclosure is referred to as 360 degrees of contact. Due to plastic's inability to block EMI, there is an understanding that there will be gaps in the ground ring contact around plastic connectors. Between optional component add-ons for signal filtering and external grounding combinations, the systems are equipped for continued experimentation after initial research. Ensuring the designs are optimized for the sponsor's long-term use required close collaboration with the sponsor and multiple design revisions. PCB2 will output 15 watts of power, so the ICs and switching transistors will be susceptible to overheating. To keep the testing environment free of excessive interference, forced air was not allowed. Enclosure geometry and heat dissipating strategies are essential to protecting the components from burning up and create a need for more precise features on the conductive enclosure.
Diving deeper into the main features of the project, we examine the first PCB. PCB1 uses a K-type thermocouple and banana plug cables to read temperature and voltage measurements respectively. Banana plug connectors are also utilized to power the board, as well as communicate with a PC resting outside of the EMC chamber. The communication type used to encode the data is Universal Asynchronous Receiver Transmitter, or UART. To isolate the device under test from EMI disturbances outside of the testing environment, fiber optics carry the UART signal out of the testing chamber before interfacing with a fiber box and breakout board to convert the signal to USB communication to connect to the PC via USB-A connector. The PCB1 series of designs focuses on the effects of grounding impact on analog measurements. As seen in this image, there is exposed copper lining the perimeter of the board. This is done on the top and bottom layers to achieve the required 360-degree contact to the enclosure. The variants of PCB1 will be tested for radiated and conducted immunity to the levels specified in the ISO 11452 standard respectively. There are multiple functions that remain the same between all PCB1 variants. An MSP432 microcontroller is used to handle and transmit data. Its internal 14-bit ADC is used to measure the analog voltages through banana plug connectors, while an external cold junction compensated 12-bit ADC chip handles the input voltage of the thermocouples for temperature measurements. The MSP receives data from the MAX6675 ADC via SPI and transmits both measurements to a PC terminal via UART. The input voltage to the PCB is provided via banana plugs, and an LDO is used to regulate the temperature input voltage from 5 volts to 3.3 volts. The analog measurement board has 7 individual board variants, meaning that there are 7 PCBs, each with unique combinations of analog trace routing style and layer, grounding method, and grounding layer geometry. The first 4 variants study differential versus single-ended measurement signals and microstrip versus embedded trace usage. Variants 5 through 7 utilize single-ended signals with a study on 2 methods of analog and digital split ground geometries, with an additional insight on the effects of using vias to repeatedly switch routing layers, as seen on highly dense PCBs.
The power board, or the PCB2 series of designs, focuses on the effects of a few methods of routing a power delivery network. Again, the exposed ground around the perimeter of the board is implemented for 360 degrees of ground contact. There are a total of 3 variants for this board. These variants will then be tested for radiated and conducted emissions for CISPR 25 standards respectively. The LM5175 voltage regulator IC on this board is used with the synchronous buck-boost DC-to-DC converter topology to step the input voltage down from 12 volts to 5 volts in our application. The TPS25740 power delivery IC monitors the output for overcurrent conditions and manages the power output based on the voltage and current requests through the USB Type-C interface. To draw the required 15 watts from the power board, a thick film resistor connected to a heatsink is interfaced with a small breakout board that houses the USB Type-C connector. The breakout board allows for a pseudo communication between the load and the PD chip to request 5 volts at 3 amps. Each of the 3 variants of the power board utilize the same layouts, except for the main power trace from the output of the buck-boost regulator to the output of the USB Type-C connector. Variant 1 uses a discrete trace routed as a microstrip on top layer, while variants 2 and 3 isolate the power onto the 3rd layer. Variant 2 uses power planes across the entire layer, and variant 3 uses small power planes that can be compared to thick and discrete traces.
Each PCB may be outfitted with either a conductive enclosure, machined from 6061 aluminum plate, or a non-conductive enclosure made of 3D printed nylon and PLA. The conductive enclosures allow the boards to be grounded to the enclosure by means of conductive mounting standoffs and/or contact with exposed copper on the top and bottom layers of the boards. The non-conductive enclosures mimic the use of low-cost plastic casings for designs that strictly house the boards with no additional EMI protection provided. The conductive enclosure offers EMI shielding for designs that cannot pass EMC regulations on their own. It also provides a means to ground the circuit to the enclosure. This provides a low impedance path to divert EMI away from the device under test. PCB1 and PCB2 each have their own conductive enclosures, which are compatible with all variants of their respective boards. As seen in this exploded view, a thin strip fabric over foam EMI gasket outlines the perimeter of the top and bottom of the board to touch off on the exposed ground trace, which is used for 360 degrees of grounding contact. Aluminum plates were milled using a CNC machining center. In selecting aluminum, the conductive enclosure provides a lightweight solution that is also easy to machine. The boards will be mounted to their enclosures using swappable hex standoffs. Zinc-plated brass standoffs may be used to ground to the enclosure for EMI protection. On the other hand, nylon standoffs may be used to isolate the board from the enclosure if additional EMI protection is not needed. To keep the testing chamber free from additional EMI due to a running fan, extrusions from the top of the enclosure are also used for conductive heat dissipation on components that are expected to heat up. Threaded fasteners are used with a conductive gasket between enclosure halves and on connector interfaces to fully seal the enclosure. This ensures that minimal EMI is allowed to leak in. The design feature is also in compliance with the required 360 degrees of grounding contact. The non-conductive enclosure simply houses the boards with no shielding from EMI provided. This represents a low-cost housing for a product developer who has a well-designed PCB which does not need additional EMC solutions to pass regulations. As with the conductive enclosures, both PCB1 and PCB2 have their own non-conductive enclosures, which are compatible with all variants of their respective boards. The non-conductive enclosures are 3D printed in nylon and PLA using fused deposition modeling technology. Tapered pins are used to locate and mount the boards. Vent slots are used for free convective cooling, and snap hook features are used to mate the top and bottom halves easily. Since plastic has no EMI shielding properties, the connection interfaces are open-ended slots. To reiterate, this design represents a housing solution for customers whose PCBs pass EMC regulations on their own.
Between the various combinations available to ground boards to the conductive enclosures and the dozens of signal filtering component options, this project provides E3 with long-term learning tools to continue the experiment with and further understand the effects of design decisions on EMC performance. The fastener tool sizes and enclosure geometry allow for quick, single tool changeovers between variants to maximize testing time. Utilizing 12-bit and 14-bit ADCs for temperature and voltage measurements respectively in the analog board design provides a means to observe small effects of EMI and grounding methods on EMC performance. The use of USB Type-C in the power board design makes it desirable for companies to investigate test results once published, as more and more products are switching to this relatively new and versatile connector type. Additionally, our testing process is designed to mimic a customer coming to E3 for consultation, where variants will be initially tested with no filtering or shielding to determine baseline EMC results. The following test mode adds the conductive enclosure for EMI shielding on designs that failed EMC regulations on the baseline test. The final mode utilizes filter components and full ground connections to the conductive enclosure for maximum EMI protection on the worst performing designs. On the analog board, the pad to plane connections are direct, so any pin connected to ground is entirely connected to top layer ground pores. This creates difficulty in removing and adding components for signal filtering because the entire ground port dissipates heat from the pad, making it harder to heat up with a soldering iron. Additional revisions could utilize thermal relief connections to minimize this effect. However, this is a trade-off for a lesser ground connection. Current variants have minimum silkscreen component labels, some of which are easily confused with the wrong component. Also, the component naming scheme is currently the easiest way to identify the variant. Next revisions should have more clearly placed component labels with additional variant labels, company logo, and connector labels. It was difficult to receive supplier support when working with the chosen PD chip because it has been designated as not recommended for new designs. A future revision could utilize a newer IC for likely enhanced performance and vendor support. Lastly, the MCU chosen for the analog board design has an excessive number of pins and peripherals for this application. This creates unnecessary struggles when soldering on the IC because it decreases the pin pitch increasing the probability of short circuits during the build process. Once again, this is 2021's Project Team 5 at Grand Valley State University. Our team would like to thank the staff at both Grand Valley and E3 Compliance for presenting us with this learning opportunity. Thanks so much for watching.